Hi, this is Tom Goddard, and today I'm going to be discussing a paper regarding thermal modelling in mountain bike air shocks. This paper was presented by Redfield at the 8th Conference of International Sports Engineering Association. Mountain biking is a technical sport with high reliance on equipment. Mountain biking is continually evolving, with faster speeds and more difficult terrain. This brings a progression in equipment. The figure seen on the slide shows the location of the front and rear suspension systems. In the past, coiled springs have been used to achieve suspension, but in most designs currently, air suspension is used. This brings clear benefits including weight and adjustability of the system. Some issues arise from the air shocks relating to the thermal effects. These are more pronounced on the rear suspension due to smaller size and being shielded from airflow by the frame. Examining the rear air shock in more detail, the energy generated from the movement of the bicycle frame creates heat in the damping fluid, transferring to the damper body. As seen in the figure, the damper body is encapsulated by the air spring, making heat difficult to escape. The result of this is air shocks cannot be used in continual high loading situations such as downhill racing and extended downhill riding. Also, as a result of the heat dissipation, the performance of air springs is greatly influenced by temperature. In order to examine the thermal effects further, a model was created incorporating the air spring and frictional thermal effects. However, do not include the damper effects. In the shock, air volumes compress and expand, altering heat energy. In the diagram, the Q dot terms are heat flow terms, with the heat transfer achieved by means of convection and conduction. The heat transfer terms include heat flow to the damper and shell from frictional effects, heat flow to positive and negative air chambers, and also heat flow between the shell and atmosphere. A bond graph allows the visualization of the dynamics of the mountain bike shock, including energy storage and power interactions. Starting from the center, the R is heat dissipation to the damper, shell, and positive and negative air chambers. The solid lines denote mechanical power transfer, and the dashed lines denote heat transfer. Heading upwards from the R, the C represents storage in the air chambers, and the TF represents transformation due to friction and damping. Heading down from the R, heat dissipation to the damper and shell is stored, and the source elements, represented by the SF, also have heat flow to the damper and shell. From the bond graph, first-order differential equations can be derived using air volumes and also heat energies as the state variables. These equations were not presented in the paper. The commercial code Mathematica was used to solve the system equations and plot the results. The input to the system is a sinusoidal displacement with varying frequency and hence varying maximum speed. This is consistent with the standard testing inputs for mountain bike rear shocks. In the simulation, speed, friction, heat transfer resistances, and initial temperatures were examined. The force compression plot for frequencies of 0.643 and 254 cm per second are presented in this slide. 3 different heat transfer regimes have been plotted. The isothermal and adiabatic regimes turn out to be independent of shock speed, which is an interesting result. This can be seen by the same shape for each regime for both speeds as seen in the plot. In the top plot, a looped curve, indicated by the dashed lines, is for a realistic conductive and convective heat transfer regime. It was hypothesized that the area enclosing this loop represents the energy lost in a single cycle due to heat transfer. In all cases of the simulation, higher speeds result in a stiffer response and a lower steady state behavior. The stiffer system can be seen in the top plot with increasing forces required for a given compression. This is a result of the increased energy in the system, with the heat having less time to dissipate from the shell. Compared to an experimental set of data in qualitative terms, the results were consistent for the first half cycle, as seen by the similar shape of the two plots. Differences in experimental data include the addition of damping in the system and also seal friction. The seal friction results in the vertical movement of the lines, which is different to the top plot, where the lines start from the same point. The top plot shows the steady state behavior for one half cycle with increasing shock speed. As the speed of the shock increases, the steady state value decreases. This is due to the reduced air volume in the air chambers relative to the first half cycle. The lower plot shows the increasing stiffness of the rear shock in response to an increase in initial temperature. This plot shows the shell temperature response. The sinusoidal band of temperatures shows the increase in temperature due to compression of the positive air chamber, followed by a decrease due to expansion of the negative chamber. Looking at the bigger picture over a long period of time reveals an increase in temperature, with steady state met by 600 seconds. The key findings from the analysis of the rear shock include the stiffening of the shock with increasing cycle speed, as well as an increase in temperature. Another key finding was the prediction of time constants for reaching steady state cyclic temperatures in air volumes and in the shell or the body of the shock. The experiment carried out has been valuable in the modelling of rear shocks. In order to gain a better understanding of the operation, more detailed analysis in the future could include the addition of hydraulic damping to the system dynamics, something that was neglected in this experiment. Also of benefit would be the examination of how air volumes increase the heat transfer resistance of the system. Thank you for listening to my presentation. I hope you enjoyed it.